Hi everyone. So in this video we basically resume and finalize the discussion of batch normalization by basically discussing the main challenge with it, right? So batch normalization, the idea is that in every training iteration you normalize the statistics of the output of every layer with respect to the mini batch, the considered mini batch, right? So you subtract by the mean and then you divide by the standard deviation to have zero mean and unit variance. Now, the problem is that when you normalize the first and second order statistics of every layer, you deprive basically the network from applying linear transformations in these layers, right? So no matter what the network does, no matter what the parameter updates are, you are guaranteeing the normalized first and second order statistics. First order statistic means the mean or the average, and second order means the variance for every output unit of every layer, right? Of every hidden layer. So that becomes that could be a catastrophic problem if we cannot learn any linear transformations in the network, but thankfully we can still, in the output layer, we can still apply linear transformations, right? So it's not that bad actually, but the problem is that you actually change the expressive power of the network, right? So after batch normalization, the network becomes a different network. It's less capable than the original network because linear transformations can only be learned in the last layer, in one layer, and all the intermediate layers are basically learning nonlinear statistics. So the tweak or the way to alleviate this problem is basically to add back linear transformations through two new parameters for every layer, right? So we had before this h prime. So h is the matrix representing the unit activations across all examples in a mini batch for one layer, right? So across all examples in a mini batch per unit, and then all units in one layer, right? And then h prime is the normalized matrix after batch normalization. Now this h prime, we replace it by gamma h prime plus beta, and beta basically will add mean values or first order statistics that are different than the normalized values, and gamma will add second order statistics that are different from the normalized value. And gamma and beta are new learnable parameters, and you have a gamma and beta per layer, right? So for every layer you add these new learnable parameters, which are the gamma and beta. Now, and therefore, if you do that, then you maintain the expressive power of the network, because in every layer you can learn linear transformations. Now, an intuitive thing that comes to mind here is that why did we do batch normalization in the first place, right? So you first remove the linear transformations from every layer and then you add them back, right? And the answer is that it's true that we removed them and we added them back, but we added them back in a different form, right? So instead of the mean of the output, let's say of 1 unit at the output of the 9th layer, instead of that mean or that average or that first order statistic being dependent on all the parameters before the 9th layer, from the first layer up to the 9th, that mean depends on just one parameter that is updated directly, right? So during backpropagation, you backpropagate the coast, you compute the gradient of the coast with respect to the beta of the 9th layer directly, right? So it's a much more straightforward calculation, and it gives the network much more control on adjusting the first and second order statistic of every layer right? Without changing the parameters or without the complex interactions of changing all the parameters before that layer, right? So therefore, by doing that modification, the intuition is that you maintain the expressive power of the network, and at the same time you alleviate the main problem that batch normalization is introduced for, which is basically the complex interactions of the parameters and leading to unexpected results and changes in the first and second order statistics of hidden layer units, and basically the problem of simultaneous update of the parameters that lead to unexpected results. So this is a much more controlled operation now, because the statistics of every unit are updated through the first and second order statistics are updated through explicit parameters that are independent for every layer. Sounds good. So it's important to note before concluding the discussion on batch normalization that it's still an open and very interesting area of research of why batch normalization actually works, right? So this is really an approach that is introduced backed by intuition, and its success is empirical, right? And empirical evidence. So there is still a lot of work, and it's an open research problem as to proving basically the reason behind why it works. The last thing I want to say is basically a small note, is that since we have this beta here that introduces a bias for every unit, right? So if you do batch normalization, and if we do this learnable parameters per layer, which is the default implementation for batch normalization, then actually the bias, the original bias units, the original unit bias parameters are no longer needed, because you would have redundancy, two parameters that are learning the bias for every unit. Thank you.